Section 9.5 is entitled Tests Involving a Proportion. Just as in Chapter 8, we started with estimating mu and moved over to working with p, the population proportion. In the same way, we have started our look at hypothesis testing with problems that involve mu, and now we're back to p again. So what's our motivation for a problem of this sort? Well, imagine, and this is an awfully timely example, let's say that Allentown's Unemployment Compensation Office is making the claim that they are receiving too many incomplete applications, that they're up now to 47% of the applications they receive are missing important information. And in order to help the unemployment applicants, those out of work, they are requesting an additional 2 staff members to assist applicants in completing the forms correctly. How can the funding agency test the claim that 47% of applications are incomplete? Well, this is a problem that we're not going to solve, this one in particular, but this is the kind of problem that we could solve. Let's set up our background information. First off, since everything that involves the population proportion that we are working off of, hoping that we have the binomial distribution, we need to make sure that those conditions are satisfied, that n times p is greater than 5 and that n times q is greater than 5. Those are required for this method. In all of the problems that I'll be giving you, that will be the case. So you do not need to worry about that, but keep in mind that it is necessary to show that these conditions are true. And so, as we've done before, we will define p hat as r over n, successes over the total number of samples, and let that be a point estimate for p. And further, we know that the distribution of these p hat values is well approximated by a normal curve, where the mean is mu and the standard deviation of sigma is as shown on the screen. That the mean is equal to p, and that the standard deviation is equal to the square root of pq over n. These are things we've seen before. Our null and alternate hypotheses really haven't changed a whole lot as far as what they look, except now instead of the null hypothesis being mu equaling a number, they're now reflected as p equaling a number, regardless of whether that's a left-tailed, right-tailed, or two-tailed test. In all case, the null hypothesis is that p is equal to k. For a left-tailed test, the alternate hypothesis is that p is less than k. For a right-tailed test, it's that p is greater than k. And for a two-tailed test, it's that p and k are not equal to each other. Now, because p represents a probability, k also represents a probability, and so we would expect k to be somewhere between 0 and 1. And I guess, technically speaking, it could be 0, but that would make for a very boring problem. Technically speaking, it could be 1. That would make for a very boring problem. So we're going to focus on k being in the middle there, that it does not include the endpoints. The test statistic formula that we use, we're back to z, and we're back to z with a z formula with p hat and p. It's the same formula that we've used before. Numerator is p hat minus p, and the denominator is the square root of pq over n. P hat, p, q, n, they all have the same meanings that we've seen them before. We haven't changed anything. Our critical values are z sub 0, so they're the same that we used in section 9.2. If you'd prefer to refer to table 6, as you were doing in section 9.4, you'd be looking at the infinity row on table 6, the very, very bottom row. And so from here, it's the same process that we've done before. We'll compare the z-score that we get to the critical value, or for a two-tailed test, the critical values, and make a conclusion in exactly the same way that we've been doing before. So here's our example. A team of eye surgeons has developed a new technique for a risky procedure to restore the sight of people blinded from a certain disease. Under the old method, 30% of patients who underwent the procedure recovered their eyesight. Suppose this new technique has been attempted 225 times with 88 successes. Can we justify, at a 1% level of significance, the claim that the new method is better? Well, be aware that the p that we are targeting is the 30%. So our null hypothesis will be that p equal to 0.30, that there has been no change. The alternate hypothesis is that there is a change, and specifically that the change is for the better. So our alternate hypothesis is that p is greater than 0.30. Since this is a greater than statement for the alternate hypothesis, this is a right-tailed test. And when we say alpha, we really are referring to alpha single prime. At a 1% level of significance, alpha single prime being equal to 0.01 suggests that z sub 0 is 2.33, positive 2.33. Let's build up to a z-score now, knowing that we need to exceed 2.33 in order to reject the null hypothesis. P hat is r over n, 88 successes out of 225 trials, so we have a p hat value of 0.39. Find the z-score. P hat of 0.39 minus p of 0.30, there's your numerator. Denominator is square root of pq over n. P is 0.3, q is 0.7, and there were 225 patients as part of this test. We get a z-score of 2.95. Compare that with the critical value that we were looking for, 2.33. We have exceeded that. 2.95 is greater than 2.33, and as a result, we will conclude that we should reject the null hypothesis. And we would make the statement that the new method appears to have improved the patient's chances for eyesight recovery. Under the old method, it was 30%. The new method, we were observing a 39% success rate, and with the z-score of 2.95. That suggests that this is not due to chance, that something has indeed changed. Or at least we seem to believe that something has changed. Okay, this one is yours. A botanist has produced a new variety of hybrid wheat. Botanist knows that for the parent plants, the probability of germination is 80%. The probability of seed germination for the hybrid variety is unknown. The botanist claims that it is 80%. To test the claim, 400 seeds from the hybrid plant are tested. It is found that 312 of them have germinated. Use a 5% level of significance to test the claim that the probability of germination for the hybrid is 80%. First things first, we better settle on a null and an alternate hypothesis. The null hypothesis is that P is 0.80, that the probability of germination for this hybrid is 80%. Our alternate hypothesis is that it is not. And so the alternate hypothesis is that P is not equal to 0.80. This gives us a two-tailed test with alpha at 0.05. And that is alpha double prime, since we have a two-tailed test. The rest of this problem is yours to do. The video will pause and give it a try, and we'll come back together in a minute and see how you did. So a two-tailed test with alpha being 0.05 tells us that we have the two-tailed test tells us that we have a positive and a negative critical value at a 5% level of significance. That means plus or minus 1.96. Our p-hat value, our observed probability, our empirical probability, is 312 successes out of 400 trials. That means that p-hat is 0.78. Calculate z as p-hat minus p in the numerator, 0.78 minus 0.80. And the denominator is square root of pq over n. P is assumed to be 0.8. Q then will be 0.2, 400 trials. Plug everything in. We're getting a z-score of exactly -1. Is -1 less than -1.96? No. Is it greater than positive 1.96? Again, no. How can a negative number be greater than a positive number? It doesn't work. So because it's no and no, we are failing to reject the null hypothesis. And we will make the claim, we will make the conclusion that there is not enough evidence here to suggest that the botanist's claim is incorrect. We are not proving, as I've said before in these videos, we are not proving that the botanist is correct. We're just saying that we don't have enough evidence to say that he or she is wrong. And so we fail to reject the null hypothesis. There's not enough evidence to say that the botanist's information is incorrect. Here are some problems for you to work on.